I want to point out some design issues, some challenges with sensors design and applications. For some sensors, you need to calibrate to relate the measurement to physical phenomena that can increase manufacturing cost. Just one thing, if you use your compass in your compass function in your smartphone, from time to time you may find that the compass is not accurate. And so to solve the problem, you probably have to rotate your smartphone for a few times and then just get the sensors recalibrated in that way. Also, non-linearity. Some of the models will assume, for example, the accelerometer model will assume the string property and the damper property, they're all constant. That might not be true in certain situations. So that correction might be required. And to address those problems, digital feedbacks can be used to keep the operating point in linear region. We're going to talk about sampling and aliasing, shortly. Also noise and other challenges. Sensor calibration. We use a fine sensor model that captures the sensitivity and bias. And using this model, we can choose to fine-tune or calibrate these properties. We can use this as an example. This is an accelerometer from analog devices, and we can see that this is just a capture of the data sheet. There's let's see here. You can see that the parameters listed here, including the measurement range of these sensors, and for this is a 3-axis accelerometer sensor. The measurement range is typically 3.6 G plus or minus, because you have opposite directions, and there are alignment errors could be present. Package alignment error of plus minus 1. The intra-axis alignment error plus minus 0.1 degrees. And 0G bias level. Also, you will have voltage output from the sensor to indicate the readings. At 0G, the typical voltage output is 1.5, and the minimal is 1.2, maximum is 1.8. So that's one thing you need to kind of calibrate to get a sense that where is this 0G indicating. So once you measure that and know that voltage, then you can start from that point to measure the other to put into use to measure the acceleration. So that's one way to calibrate using this bias value that you can refer to in the data sheet. Okay, aliasing is related to sampling. I will talk about sampling also when we discuss the analog to digital converter. So when you have these sensors, oftentimes they produce a voltage signal, and many sensors, they are producing continuous voltage signal as output from the sensor. To process these signals, you will need to sample them so that you can have these discrete values for digital systems to process. That's called sampling. And what we're showing here is a phenomenon called aliasing. Sample data is vulnerable to aliasing, which means that the high frequency components masquerade as low frequency components. Okay, so let's look at this diagram here. This is the time, so horizontal is the time axis, and the vertical y-axis is the amplitude of the signal. What we are seeing here, actually, there are two signals. One is 800, I believe it's 800K. Let me check that quickly. I'm sorry. So the higher frequency, this signal is at 9 kilohertz. Okay, and what's showing in the dotted line, this is another signal, sinusoid signal, and the frequency of this signal is just 1 kilohertz. Okay, if you count the number of cycles, this is actually 9 cycles, and versus this is the another 1 cycle for the 1 kHz. So again, this solid line, solid curve, this is 9 kilohertz signal, and the dotted line is 1 kilohertz signal. What we're doing here is that we are taking samples, and the sampling rate is 8,000 samples per second. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this 0.001 second, we're taking 9 samples. If you look at this black dot, this is the value we will get if we sample at 8,000 samples per second rate. And what we're showing here is all these dots, we have these two signals overlap, right? This is a 9 kHz, this solid line, solid curve, and the dotted sinusoid wave is the 1 kHz. And all these samples, they overlap on the same dot for these two signals, which means that by taking these samples, we have no idea what is the frequency of this signal. It could be that it's from 1K, it could be from 9K hertz. And this is called aliasing. And that's not good because you essentially, we didn't get a whole picture of the signal. Either of those, we didn't get a whole picture. So we should really be careful when we model the signal source and getting these samples from these analog signals. Even for digital signals, we also have similar effect where if you have, here example, we have two images, and the sampled images also show aliasing effect because you can see the patterns edges appear as the side effect. You will see this blurring and images as opposed to a clear image of what's captured in the image sensor. So that's the the concept of the aliasing, and we will talk about when we do the sampling using ADC, how we need to decide the sampling frequency to address this aliasing problem. Also, when we work with sensors, there can be noise and signals mixed with signals. We need to perform signal conditioning. And specifically, we want to use filters to try to eliminate or minimize the impact of noise signals. In this example, you have signal, this XD, is mixed with noise signals, this XN. And because useful signals are typically narrowband, so we know them at certain frequency, whereas the noise signals could be wideband, so it's going to be spread over certain frequency. Using low-pass filters, we can take advantage of this, these filters to dampen the noise signal and try to enhance the impact, enhance the effect of the useful signals. Because the way we really want to have a good signal as opposed to the noise is to have the amplitude of the useful signal as high as possible, whereas the amplitude of the noise signal as smaller as possible. As a result, we will be able to get this higher signal to noise ratio. So this SNR is very useful in a lot of the signal processing domains, including sensor designs. We would like to have the higher signal to noise ratio, and that can be done using filtering. Sensors are physical devices, so they are subject to malfunction faults. They can wear and tear. They may have manufacturing defects. And so we cannot assume that all sensors on the system will work correctly at all times. Depends on your application. If you, like in our second lab, if you design a game controller, your sensors should work all the time, but if it doesn't work, or it doesn't work for that second or a minute, that's probably fine. You can just give up the game and do something else. But if the sensor is on a critical mission, on say an airplane, then you have to be mindful how you can design your system to accommodate, to cope with such faults in sensors. A typical solution is to use redundancy. So you have multiple sensors to measure the same thing and try to get the readings from all these sensors and make a decision. However, it sounds good when you have multiple sensors, but you should also be careful how you use those sensors. In the slide, the Professor Lee and Seshia, outlined this example. This is a Qantas Flight 72 that was flying from Singapore to Perth on the 7th of October 2008. This is an Airbus A330 airplane. It started pitching violently. Unrestrained passengers hit the ceiling. 12 serious injuries. It's a big accident. Now, of course, in the recent several years, Boeing had also issues with their airplane and caused actually, plane went down in 2 occasions, and that's also related to sensors. Well, not necessarily sensors itself, but also control systems. This is the case on the A330 flight airplane. In this flight, they had a few sensors, 3 sensors to be exact, 1 on the left, 2 on the right of the nose of the machine flight. aircraft. And these sensors didn't work all the time, and it may just happen that the sensor readings went too off. So the controller software tried to deal with these inaccuracies, but because it ignored the sensors readings, because it thinks one of the sensors didn't work, whereas the other one, didn't work well either. So it actually, the controller used the wrong information from a malfunction sensor, and the system actually caused the plane to do violent pitching, and then some very serious troubles with the flying the airplane. So if you're interested, there are a lot of details you can look up on the internet about this incident. But the story is, you have to be able to design your system to accommodate sensor failures. And that's not just the sensor itself or redundancy of sensors. You have to be mindful about how your control software handles such unreliable sensors. Okay, so we went through these several points. Now let's look at some examples of actuators. One of the most widely used actuator is the motor. This is an example of robotic hand. This is the bionic hand from Touch Bionics. This was in 2007. Of course, nowadays you can find many vendors of such robotic hand. But at that time, it had 5 DC motors to control these fingers' movement. These motors were very precise, and controlled by the software, these fingers can be manipulated to grab a paper without crashing it, and or turn a key in a lock. And it's controlled by pulses of a user's arm combined with autonomous control chip to adapt the shape of whatever it's grasping. So this is a good example that shows how actuators work. Actuators essentially to convert electronic signals or cyber signals into physical quantities. In this case, is the force, so grabbing an object. And there can be many other different actuators. This is just one of those many examples. Okay, so before I talk about this pulse modulation, because when we deal with cyber systems, when we design our software to control the system, we all, most of the time, we do digital processing. We do the computation in terms of digits, and when we send out the controls, try to apply that to a physical quantity, we also use digital format. So it'll be hard that you will need to apply a continuous quantity. Let's say you want to move one thing, move the voltage continuously from 0 to 5 volts. Oftentimes you have, you can output a 0, that means 0 volt. And if you output a 1, it will be 3 volt if your VCC is 3, or 5 volt if your VCC is 5. So there's sudden jumps of these digital output. And it's not that straightforward to generate a precise continuous signal so that you can use to apply on some physical property or physical quantity. So that's why we say here, delivering power to actuators can be challenging. For some actuators, for example, LED, believe it or not, is an actuator because you are applying power to this dial and it's emitting light in certain colors. So it's an actuator. And you can turn this LED off. That means you can just output a 0, and that'll be off, assuming that you connect the LED in a certain way. And you can turn this LED on. You can output a 5 volt. So that's easy to do. But if you want to dim the LED and you want to be able to control the intensity of the LED continuously, and that's a different story. And that's not easy to do without this pulse width modulation. The pulse width modulation is a method to effectively deliver power and change the power delivery as you desire, in more like continuously. Using LED as an example, if you give it 5 volt, the LED will be the brightest. If you give it 0 volt, it'll be the dimmest or the darkest. It's off. But if you want to give it effectively a 2.5 volt, maybe somewhere in between, and you can, if you want to change the intensity of the LED, you have to basically turn the LED on and off rapidly. Because if you turn the LED on and off rapidly, essentially you are delivering not the full power, not the 0 power, but some partial power to this device. Okay? And that's how this pulse width modulation is trying to do here. Imagine that this voltage is applied to a LED. So the full voltage is 1 volt, and the lowest will be 0 volt. And I can turn this voltage on for a shorter period of time and then shut it off. And then on for a short period of time and then turn it off. And I can make sure that I only turn the voltage to 1 volt at 1/10 of the cycle. If I can do that, that essentially to say I want outputting roughly not exact 10th, but some portion of the power to the device. And this 10% is what we call duty cycle. This kind of control is useful for devices that can tolerate rapid on and off. LED is such an example. The other example is the motor. So DC motor is actually another good example that can tolerate rapid on and off. And motor itself has the coils on the, running around the core, and if you apply a voltage, you have current in the coil, and when the coil is encapsulated into the case, which has a permanent or electronic magnet, then the coil will start to change if you apply the voltage. And also the coil has its inductance. That's kind of the opposite, trying to slow the movement down because of the magnetic field. So when you apply on and off control to this motor, the motor will turn, but even if you turn it off, will still have the momentum until you drive it next time using the next PWM pulse. So in this way, the motor can turn continuously. So what I explained earlier is that this PWM, pulse width modulation, as illustrated here, is a good approach to power the actuators, and it's particularly useful for devices that can tolerate rapid and on and off controls. And this way we can deliver the power to control these actuators efficiently. So this is what I was describing about the motor. Electrically, we can model this device as such. So the V is the turning speed of this coil wound around the core of the motor, and R is the resistance of the coil, and IT is the current at this moment, and L is the inductance of this coil, and this di over dt, this is the changes on the current, and this K subscript B is the so-called the back electromagnetic force constant. That's due to the coil when you turn the coil, actually, because it's inside the magnetic field, so it's actually generating the opposite current, like a generator. So that's the effect of the back electromagnetic force. From the mechanical side, this model follows the Newton's law. So it has its movement inertia is the will equal to the torque and friction and the load. So it has the mechanical model and follow this principle. Okay, so what we have talked about so far are the sensors, and mostly sensors, and we did talk about briefly about actuators. We explained from the model perspective how an accelerometer works, and we briefly discussed about the models, the bias, and other properties. And we talk about the faults that you can encounter in sensors, which are physical devices. And so that's what we have discussed so far.